Stephen Hawking died 5 years ago. Now, his family confirms the rumors. In his lifetime, Stephen Hawking's contribution to the field of theoretical physics made huge impacts that still shape and inform a lot of studies today. And after the brilliant scientist passed in 2018, there's been some really interesting studies based on his findings, and the outcome will leave you blown away. His unfinished works had a lot of scientists on the hook for years after his death, and since completing some of these tasks seemed mid-wrecking, there's been various speculations by both scientists and other enthusiasts. But the recent revelations will have you blown away, as the family has decided to clear the air by providing clarity on some of the gray areas. Welcome to Declassified Theories. Join me as we explore the mysteries of the universe. Hawking was fascinated by black holes, and he made some significant contributions in the area of study. He believed that black holes emitted some kind of radiation which suggests decay of some sort, as opposed to the idea that they were infinitely expanding and might one day void the universe into itself, given the massive gravitational pull they have. Now, for a better understanding of Hawking radiation, we must first look at the concept of black holes. So, what exactly is a black hole? Some might ask. Well, think of it as a region in space where gravity is so intense that nothing, not even light, can escape its gravitational pull, hence the name black hole. They're believed to be formed from the remnants of massive stars that have exhausted their nuclear fusion fuel and undergone gravitational collapse, leaving a dark mass with a gravity beyond imagination. Black holes are known to have areas known as the event horizon, and these are boundaries beyond which nothing can escape. It's believed that once an object crosses this threshold, it is forever trapped within the black hole with no way out. The singularity lies at the center of a black hole, which is a point of infinite density, where the laws of physics as we know them are believed to be, well, very much inconsequential. Where does Hawking really fit in all of this? In 1974, Hawking made a groundbreaking postulation that black holes don't just gulp everything on their path infinitely, but emit some kind of radiation which the black hole has to compensate for only through its mass, which will eventually result in a total depletion of the black hole. And the equation to solving this problem presently adorns his gravestone at Westminster Abbey. Hawking, despite suffering from ALS, made remarkable contributions to the field of theoretical physics, which still holds the interest of researchers years after his death. With the limited knowledge of the black hole available to advanced physics, it was believed that nothing could escape from a black hole. However, Hawking, combining the principles of quantum mechanics with general relativity, showed that black holes aren't truly black after all. He postulated that they emit a form of radiation, which came to be known as Hawking radiation. Hawking radiation challenges the conventional notion that nothing can escape the clutches of a black hole. According to Hawking's theory, particle-antiparticle pairs are constantly being created and annihilated at the event horizon. Occasionally, due to quantum effects, one particle from the pair may escape while the other falls into the black hole. This causes the black hole to compensate for the lost particles and thereby lose its mass in the process. And eventually, if this goes on long enough, the black hole will eventually cease to exist. These particles that find a way to escape the event horizon give rise to what is known as Hawking radiation. Due to this radiation, the escape of particles gradually causes the black hole to lose energy over time, ultimately leading to its eventual evaporation. Remarkably, as we've stated earlier, Hawking radiation postulates that black holes can actually shrink and disappear entirely, contrary to the previous belief that they are eternal. This postulation isn't one without complexities. The concept of Hawking radiation gives rise to a fascinating paradox known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed. Yet, if a black hole evaporates completely, all the information of the matter it engulfed would seemingly be lost, meaning that it goes against the laws of quantum mechanics, which states that information about any physical process can be recovered from a reversal of the process. This has so far created a void in theoretical physics, which needed to be filled and threatens one of the most widely accepted theories in physics, which is quantum theory. Many scientists have gone in search of a resolution to this paradox, and it's still very much a subject of active research. And there's been some breakthroughs in this search for some that have attempted to look. Many physicists believe that the information is encoded in the outgoing Hawking radiation, but extracting it is an incredibly complex task as the particles are highly elusive. And to many, resolving their paradox is crucial to understanding the fundamental laws of the universe we live in, and also an opportunity to uphold some of the basic laws like quantum mechanics and general relativity, which have formed the foundations for understanding various universal concepts in theoretical physics. The radiations that these black holes emit give out very low signals, and as of now, detecting Hawking radiation directly remains a challenge due to its incredibly faint nature. The radiation emitted by astrophysical black holes is extremely weak and gets overshadowed by other sources. However, scientists are optimistic that future space-based observatories and technological advancements, such as the recently launched James Webb Telescope, may enable us to observe the elusive Hawking radiation. So far, there's been some really interesting moves at solving the paradox, and two of the most prominent are the quantum hair and the development of quantum gravity models. In 2020, a team of scientists from The Ohio State University, led by Samir Mathur, pushed the idea that black holes have a property known as quantum hair. And this is believed to be a set of quantum fluctuations that are unique to each black hole and that carry information about the black hole's history. If quantum hair exists, then we might have a way to access information about the black hole. If this theory holds, then it'll be a testament to these ideas. Firstly, it would mean that black holes are not completely black, but rather emit a faint glow of radiation, which could carry information about the black hole's history, and be one way to solve the black hole information paradox. And secondly, it would mean that black holes are not completely deterministic, but rather have a degree of randomness. This randomness would make it impossible to predict exactly what would happen when two black holes collided. This is still, however, a developing theory, and there's still so much that we have to learn about this quantum hair. However, the quantum hair theory looks very promising for our understanding of black holes and what goes on within them. If peradventure they do exist, it could provide a key to solving some of the most fundamental mysteries of theoretical physics. The second approach to solving the paradox rests with the development of new quantum gravity models, and this was done by a team of scientists led by Donald Marolf of the University of California, Santa Barbara. This approach proposes a new model of quantum gravity that could also solve the black hole information paradox. The idea projected here is that black holes are not completely black, but rather emit a faint glow of radiation. This radiation could carry information about the black hole's history and could potentially solve the paradox. And to better clarify this, one way that quantum gravity could solve the paradox is by providing a way for information to escape from black holes. In classical general relativity, as proposed by Einstein, black holes are completely black and no information can escape from them. However, in quantum gravity, there's the possibility that black holes are not completely black, but rather emit a faint glow of radiation. One other way that quantum gravity could help solve the paradox is by changing the way that information is stored in black holes. In classical general relativity, information is thought to be stored in the black hole's geometry. However, in quantum gravity, it's possible that information is stored in the black hole's quantum state. If this is the case, then it is possible that information could escape from black holes through quantum tunneling. There's a number of different quantum gravity models that have been proposed, and each model has its own potential solution to the black hole information paradox. However, no single model has yet been universally accepted, and the paradox so far remains unsolved. To this day, this groundbreaking theory challenges our understanding of the universe and sparks intense debates among physicists. As we continue to make moves to unravel the mysteries of these cosmic states, we move closer to understanding the secrets that lie at the heart of black holes and the nature of the universe itself. I would like to get your thoughts in the comments, and I will see you in the next video.